No, they're doing really well.
Yes, it's amazing how well they cope they really thrive in the lab, under lab conditions.
Yes.
Well, at the moment, you can see, for example, this individual tending a larva. She's grooming it, which means that she's trying to remove any sort of bacteria that might be on the surface. And another individual here is moving either a brood item or a debris in the nest. Yes, a worker here has a brood item in her mandibles and she's changing its position. This worker is feeding a brood larva, or at least exchanging food. If you recognize an individual by marking them and you follow them for a while, you'll see that they're faithful just to a particular zone in the nest. And all these phenomena are not down to somebody having a plan and telling the ants what to do.
Oh, there's no leader.
There's no leader. I think they're really great creatures, and when you study them, they really open their secrets for you. You always find something very interesting.
Okay, this is where we build stuff. This is where we build robots. We've got going here, well, for example, back here, we've got in 1951 a guy called Gray Walter, who worked at the Burden Neurological Institute, started with building simple robots. The idea was to see how you could get complexity from something which is relatively simple. And this is a recreation that we've made here of the 1951 Gray Walter robot. We've also got robots in various states of undress. The problem is with conventional robots, like this heavy-duty robot here, is that it takes a lot of batteries to make it work, and it's built of gearboxes. And long-term, we'd like to build robots that don't necessarily look like robots. There it is, moving away quite happily towards the sun. And each of these photocells is coupled to the opposite wheel. If you've got energy on both sides, then both wheels will be triggered more or less at the same speed. But when one of the sides gets into the shade, then there's more energy on this side, so the opposite wheel is triggered. That means you'll move away from the object. So as long as you're going towards the sun, it will carry out a form of obstacle avoidance, but with no brain. So we're quite interested. One of the themes of the laboratory is how dumb can you be and still be useful? So this is quite interesting.
This is a colony of the ant Leptothorax albipenis. In nature, they live in fissures in rocks, which are approximately flat, and that makes them ideal for studying the behavior of the whole colony. because in the laboratory you can house them in this type of nest made of very thin cardboard, and this cardboard is sandwiched between two microscope slides, and we can see all the members of the colony with the queen in the middle, the bigger individual, and all the brood.
Well, we're interested in robots that fly as well. These robots here have been used for trying to show that you can get a collection of dumb robots doing something smart. If you wanted a robot to follow something, we call it a beacon, it had to follow this beacon. By following this very simple rule set, one robot could follow the beacon and would get there, it would be about 40% successful. But when we added some very simple elements to this rule, we found that by putting about half a dozen of these robots together and then letting them go, the success rate really went up over 90%. So if you put a bunch of these robots together, they were collectively able to do something that one robot wasn't able to do on its own. These are robots, but they'll be part of a fleet of robots which will allow us to do experiments with self-organization. How do you get systems to build structures when each element of each robot can only communicate, say, that much, but you want to build a structure which is this big?
You can see here that smaller items seem to be in the middle of this pattern, while bigger items are on the periphery. This pattern is not the result of simply the queen who tends to be in the middle of the pattern laying eggs. We know that because when we provoke an emigration by putting a new nest close to this one and disturbing the present one so that ants go to the new nest, when they go into this new nest, they resort the brood in exactly the same pattern. The phenomenon we're interested here is how ants manage to sort their brood in that way. Why is it interesting? Because it's a collective level phenomenon. It's beyond the scope of an individual ant. By that I don't mean that the ants are stupid, but just the pattern is too big for their overview. However, without a central controller, they manage to sort the brood. So there isn't any one individual that has the whole pattern in their mind.
We know that these tiny little guys called leptothorax ants, very small ants, they're able to take brood and they sort the brood and make sort of concentric circles of different brood types. And we're really interested in how they do that, because we'd like to exploit those ideas and put them on robots. So these robots here have been designed, they're quite smart robots, but we've sort of turned the dumbness switch up, so they're pretty stupid. I'm trying to make them as dumb as possible, and yet they're able to carry out this particular job of sorting. If you look at ants, you find that they seem to be suboptimal, that you might have a whole bunch of ants taking eggs from one area and then moving it to another area. And then you get 2 or 3 individuals who decide that once it's been put down, they'll pick it up and take it all the way back and just drop it down again, which is clearly some sort of crazy behavior. It does look bizarre, but they must be doing something which is useful, because ants have been on the planet for, whatever, 100 million years, so there must be some value in what they're doing. And sure, although it may be difficult to understand what an individual is doing, when you put a whole bunch of them together, then collectively they're able to solve this problem.
We are trying to find the simple rules of behavior that ants follow. For example, they could be doing the following. They could have a rule that in the initial clustering stage, if you come across a brood item or the wall, drop the brood item that you're carrying. In the phase when they're moving on brood items away from this cluster, the rule could be pick a brood item at random and they drop it a particular length, a particular distance, yes? And we can take these rules and put them in the robots, program the robots with them, and then see whether the pattern they achieve at the collective level is similar to the pattern that we observe in the ants.
So here we've got a collection of robots carrying out 4 very, very simple rules, and in the end they're able to sort the white frisbees from the black frisbees. But they don't have cameras on board. They can't talk to each other. The first rule is, let's look at this robot here. If there's nothing around, just keep going. So that's one rule. Another rule is, if you bump into a big thing like a wall, you take a random turn. And I'm waiting for the next one. If, for example, so that's 2 rules. If you're carrying a puck and it's a black one and you bump into another puck, you take it back and you don't do that. Okay, we'll do this one. Okay, so this is the rule. If you're carrying a black puck and you hit another, a puck, it doesn't matter what color it is, you pull it back and then you dump it. If, on the other hand, you're carrying a white puck and you bump into another puck, then you leave the puck where it is. And if you carry out those rules for many, many hours, then you end up with the white pucks being pulled apart and separated from the black pucks. So you don't need a global controller, a central brain to be able to do it. You can still, and if we destroy this, the robots will carry on and resort it again. If we were making very, very small robots, I mean, the sorts of things that it might be, but this is slightly science fiction, so, you know, I don't know. But maybe you have very, very small robot systems in paint, so they can actually move within a paint material. They might be able to look at cracks on, so you paint it over a bridge, for example, and within that bridge, the paint itself has got tiny, tiny robots embedded in it which can move around, perhaps. Of course, it might be that you want to build bigger structures. You might want to have in certain operations, mining operations, things like that, on other planets. And it could be that by using lots of simple robots, it doesn't matter if some of them break down, because there are more of them. They're cheap, they're inexpensive, they offer robustness. Rather than putting all your technology in one robot, which could go wrong, you spread it around, if you like, amongst a whole bunch of robots. And it doesn't matter if a few of them don't work. Yeah, this one's just gone, its wheels come off. Okay. Could, Matt, could you go and call CB for me? So if you have one robot in 10, which is not behaving very well, that's 10% of your population. If you have one robot in 100, that's only 1% of the population. So as long as you've got a relatively small number of robots doing the wrong thing, maybe the rest of them will swamp that effect by doing the right thing.
Wilt u binnenkort in het Leidse Naturalis meer te weten komen over unieke natuurlijke constructies en vragen stellen aan de maker van deze serie? Bel dan VPRO Backstage 035 6712 585.